Hey, welcome back to Introduction to Metallurgy. This is Module 2, Weld Metal Science. This is an introduction to welding metallurgy. In Module 2, we'll dive deeper into weld metal science as we discuss heat input and the role it plays in your end results. We'll look at how weld metals are processed, different strengthening mechanisms that may have been done, and how heat input from welding can reset the whole process. Oh, and last but not least, we'll go over some common weld discontinuities so we're on the same page when we jump into carbon steel metallurgy in Module 3. And don't forget to do the activities and take the quizzes if you want to earn your credentials. Metallurgy sounds like a big science word, but in reality, it's just the study and practice of metal extraction, refining, and processing different alloys. Extraction starts the process. Most come from an ore or an oxide as part of a rock or the earth. Few metals are found in pure form, only those like gold that are considered noble metals and resist oxidation. So, metals are separated and refined using various processes. Once metals have been isolated, they're melted, mixed together, and made into shapes that we use every day. Mixing metals with other metals and even non-metals is called alloying, a process that's done to improve different properties, and we'll dive into more on that when we discuss each specific alloy in the modules. All of the processing, alloying, and working results in key metal properties, mechanical, physical, and chemical traits that factor into welding. These properties are a combination of the mixture along with the heating and cooling rates used to process the metal. Heating and cooling at different rates can change these properties. Welding heats and melts metals in the same temperature range used to refine and process the material. So the study of metals is extremely important for welding. Metallurgy works to define mechanical, physical, and chemical properties of metals and metal alloys before, during, and after processing. Long-term metallurgy includes fatigue and creep failures that occur after a product or component has been in service for a while, hopefully a long while. Overall, heat treatment, casting, forging, welding, and even 3D printing each have an effect on the metals we're working with and determine how they're going to perform in their intended application. Metallurgy is also concerned with failure analysis, the nature of various failure modes from ductile to brittle and fatigue. Most of the metals we work with start out as an ore, right? Aside from those metals that come pure like gold that don't like to oxide or form any other compounds. Most metals have a positive electrical charge, meaning they can take on and share electrons easily. They have an affinity for oxygen, which carries a negative charge, and opposites attract. So most metals are extracted as some form of an oxide that must be refined to get pure metals such as iron, aluminum, stainless steel, titanium, and others. So we extract these oxides as part of the earth. Iron ore is part of a rock, for example, and aluminum comes from a substance called bauxite, which is again basically ground up rocks on the planet. So these materials are extracted in mines and then refined through various processing to isolate and purify the parent metal. We often think of metals as being pure, but in reality, most of what we work with are alloys, mixtures of metals with other metals and nonmetals to help improve those key properties we're looking for. Steel, for example, is an alloy of iron and carbon, a metal and a nonmetal. Alone, iron is soft and ductile, but adding carbon increases strength and hardness, forming the metal we call steel. Other elements have different effects. Even the term aluminum could be referring to hundreds of specific alloys with a matrix of heat-treatable and non-heat treatable varieties. As we mentioned before, all metals form a crystal structure upon solidification. Based on the relationship to other elements, atoms, or molecules in the mixture, they'll take on a certain orientation. This crystal structure is very dependent on the heating and cooling cycles that the material's gone through from production to processing. And it's going to be a concern for us as we talk about the heating and cooling cycles of welding. Let's talk about how to strengthen pure metals. We already talked about the concept of alloying, right? Adding other materials to a parent metal in the form of a liquid so that when it solidifies, it naturally has a certain characteristic, right? Okay, so once we're done with alloying, some metals can also be heat treated. right? And when we talk about heat treatment, there's a couple of different forms of heat treatment. One is called quench hardening that we'll discuss. It's mostly effective with steel and alloys that undergo what they call recrystallization at an elevated temperature, right? And then we quench that material to lock in that microstructure. And then there's something called precipitation hardening, which might look similar to quench hardening on the outside, but something else is going on the inside. So we'll talk about that as well. It's another form of heat treating and quenching. And then if a material doesn't respond to heat treating in any way, many times we can work harden it. We're going to talk about what work hardening means too. All right, so let's beat on the drum of alloying again. We make alloys to improve the properties of pure metals. In the case of steel, we combine relatively soft iron with carbon to improve strength and hardness. We add chromium to prevent corrosion, making stainless steel. We add sulfur to improve machining, which, by the way, really makes weldability suck. And each of these elements has an effect on weldability and how metal will behave when we heat it and cool it using the process of welding. As we'll discuss, metallurgy can also have an impact on things like porosity. Let's jump into the whole process of heat treating. What are we doing with various forms of heat treatment? In general, annealing is a softening process, and it softens a material by allowing it to slow cool at a very controlled rate, like within an oven. This is generally the most formable and ductile condition of a material, right? It's going to have the lowest strength and hardness, and it's going to form an equilibrium microstructure as it's allowed to slow cool. Fast cooling or quenching would have the opposite effect. If the alloy was heat treatable and quench hardenable, it could form a very strong but hard and brittle microstructure if we're not careful, right? And that's based on carbon and alloy content. Therefore, it's very common to order material and receive it in the annealed, or what they call the dead soft condition, right? So if a material is heat treatable, sometimes we don't want to work on it in its fully heat treated state. We'd rather work on it in its soft condition and heat treat it after we're done. On the other hand, some alloys are supplied in the heat treated condition. So you're going to get that material in with some form of heat treatment done on it, right? And it's important to understand what you're working with, especially if it's a heat treatable alloy. And we'll discuss those with each material module. And if we don't pay attention, we could be having some serious issues with our after welded results. Okay, normalizing is basically the same thing as annealing, right? You might order some 1018 carbon steel in the normalized condition, which has been allowed to cool to at room temperature, right? Not in an oven. So potentially it cooled at a faster rate, and it might not be as soft as a full anneal, and it's probably going to have just a little higher strength and a little higher hardness as a result of the slightly faster cooling rate. And again, that's largely going to depend on the alloy and how hardenable it is, right? How much alloy content does that steel have, and how easy is it to achieve a hard or a hardened microstructure in some form. So cooling rate's going to have a direct effect on that. Now, for materials like steel that are quench hardenable, when you have enough alloy content, they undergo a crystal structure change when heated to a certain temperature before they melt, right? So that crystal structure is going to change and those atoms are going to move around as they go up in temperature. This is called allotropic transformation. I know it's a big word, but don't get hung up on that. Just know that this means the material, like steel, changes internally when you apply a certain amount of heat. And based on how much carbon and alloy content is in that material, it's going to change the crystal structure. And the metal can be quenched back or near room temperature, and it can lock in a new phase, right, if it's got enough of that alloy content. And that's going to be stronger and harder depending on the cooling rate or the quenching rate. Now, quenching describes the process of rapidly cooling or force cooling a metal, right? Usually done after welding or heating of some form. We're going to quench it back down, which means cool it really quickly so we can handle it. All right, some metals, especially steel, again, with enough carbon and alloy content, can be hardened this way, quench hardening. Steels can be heated to that recrystallization temperature, which is somewhere between 1300 and about 1700 degrees Fahrenheit, depending on the alloy. And then it's quenched at a certain rate to increase strength and hardness. Again, this is based on the rate of cooling and how much, right, as to how much strengthening or hardening occurs. So we often use different mediums when we're trying to achieve different levels of hardness, right? You might use oil, salt water, or a brine, or you could use pure water, right? Different quench mediums have different quenching rates. If a material is quench hardenable, this is going to form a non-equilibrium phase. In high alloy steels, it's going to be called bainite or martensite, which can form, and they're hard and very durable and wearable, but they can be brittle and be more crack sensitive. This is the primary concern when we're welding such metals because welding generates temperatures at and above the recrystallization temperature, right? We're melting the metal. So that means around the area that we melted, that's going to get super hot and recrystallize in a very localized area, which is kind of the whole issue with the heat affected zone. It is not homogeneous, it's not evenly distributed out through the metal, right? It's going to be right there, concentrated in and around and under the weld bead. Okay, so rapid cooling after welding creates the perfect scenario to create this hard, brittle, heat affected zone that can crack under the stress of heating and cooling. And that's actually what happens, right? That layer forms, and as the material heats and cools with welding, it expands and contracts. That area has nil ductility, which means when it gets pulled on or pushed on, it's not going to move, and instead it's going to crack in that area. Right? That is the whole mechanism behind underbead cracking. All right, we're going to cover this more in the steel module, and quenching is always happening in some way when you weld. So keep that in mind. The air around the weld is taking heat away, right? The base metal itself, based on how big that structure is that you're welding on, is sinking the heat away. So that makes a difference. So unless you're actually applying heat to maintain a temperature, you're seeing some form of quenching when you're done welding. And again, that's the thing. When materials are made, they're made under strict guidelines for heating and cooling rates. And when we weld on them, that stuff goes out the window, right? And then we get unpredictable results. That's what this whole class is about. Okay, so for metals that can be quench hardened, right, like highly alloyed carbon steels, the process of what they call tempering can restore toughness and impact resistance when you're done. Because as you can imagine, these materials behave like glass, right? They're fully quench hardened, and they have great wear resistance and strength and high hardness and all those properties. But during an impact, they could shatter like glass. So heating to a temperature not normally as hot as recrystallization, but warming it back up helps to maintain desired heat-treated microstructure of martensite, but it restores that toughness and it reduces the brittleness of the metal. So again, it won't shatter like glass. It also may help to relieve some of the internal stresses that were caused by welding and then heat treating or other processing that was done. And again, temperature is going to control the results. So the higher the temperature and the longer the time, the more softening will occur. Now, as we mentioned before, precipitation hardening appears very similar to quench hardening, and if you saw both of them being done, you might assume that they were actually doing the same thing. But the mechanism works a little different here. The base metal doesn't necessarily undergo an internal change. There's no recrystallization. From a solid all the way to a liquid, these materials are going to maintain their crystal structure. So we're not getting any phase change. We can't lock in a harder microstructure. There is no harder microstructure formed. So instead, what happens is alloying elements are added to this material way back when it was being made, right? That solid solution strengthening phase when we mix the metal together. And now what we're doing as we heat the metal is it is dissolving these elements more evenly on throughout the material. So as it dissolves these what they call precipitates out, It basically disperses them through the parent metal. It increases hardness, it increases strength, and then we quench it to room temperature to lock those elements that are all evenly distributed out through the material. And then there's a process known as aging, which is kind of like, we're going to say it's similar to tempering, but it has the opposite effect. We can actually gain more strength by heating the material up to some point below, right, the melting temperature and the precipitation temperature. And what it does is it helps to break those precipitates up into smaller, more isolated molecules. And as they're more evenly distributed, it helps to improve the strength even more than just precipitation hardening. Now, some metals don't respond to strengthening due to base metal or insufficient alloy content, and they have to be strengthened in other ways. Of course, additional elements could be added during the mixing process, right, for solid solution strengthening, and that way we'd have enough where maybe we could quench harden or maybe we could do precipitation hardening. But what if that's not possible when the base metal chemistry is so tightly controlled to meet standards and specifications? Or maybe because one of those other characteristics is more important in the application? Well, some of these metals can be what's called cold worked, right? Or work hardened or strain hardened, which alters the internal crystal structure, which is basically the formation or the grains that form during solidification, which are aligned microstructures, right? In smaller clusters or patterns, right? Those atoms can be compressed together and it makes the base material stronger and tougher, right? As it's able to absorb a bigger impact. Now, this isn't normally as dramatic of an increase as heat treating, but in many cases, it can have a significant effect on strength for materials that are not heat treatable, right? So weld metals can be specially formulated with certain elements that encourage the formation of small, fine grains. They call these grain refiners, and that helps the weld metal be stronger and tougher than the weld metal around it in many cases. And cold working can also be done to mechanically alter the grains, whether we're compressing it, straining it, pulling it, bending it, drawing it, any way that we bend this metal, we're seeing work hardening occur, typically during product formation. In the case of certain materials, once they're work hardened, we may want to anneal them to prevent tearing, ripping, or straining. Annealing can reverse the effects of work hardening because it allows the material to relax up at the recrystallization temperature, right? And when it does, the work hardening is reversed. So then we could go back to forming or bending or using the material in the way that we want. We just have to remember to slow cool it at the annealing rate. Okay, so welding can simulate the annealing process even when we don't want to, which can soften and weaken the material, especially right around the weld in certain alloys. And we're going to talk about hardening in later modules as we discuss individual alloys. Now, what does all of that mean for welding? Well, that's the question we're going to focus on from here on out. How weld metals behave when you weld them, based on what we know about metallurgy. Let's look at how welding reprocesses our metal. Welding takes metal back to the day it was born as a hot liquid material, right? It was carefully alloyed. It was mixed together as a liquid, and then it was slow cooled and possibly heat treated before we received it. And welding is going to melt it again. Okay, well, what could possibly go wrong, right? Well, if we analyze the weld profile, the center of the weld represents the fully melted zone. This zone was completely liquid, and an admixture or a combination, a new alloy of base metal A plus base metal B and any filler metal used in the process come together here to form a completely new alloy for the most part. As the arc travels or ends, the weld immediately begins to solidify from the outside edges toward the middle of the weld pool. Solidification occurs from the outside because the heat is being conducted away through the surrounding base metal, right, that's not as hot, and through any fixturing, tables, clamps, or anything else that's in contact with the metal. I like to say it forms a horseshoe as you're whipping along. which gives you something to look for. As you watch your weld solidify, you're going to see a horseshoe form around the outside on the back of the weld on the opposite side of the direction of travel. And that horseshoe is going to let you know that that weld is starting to solidify. All right, now the next area outside the melted zone is called the heat affected zone, or the HAZ. This area got hot, like almost hot enough to melt, and certainly hot enough to change its crystal structure and to excite precipitation elements, and definitely hot enough to alter some of those base metal properties. Remember, even annealing occurs above the recrystallization temperature, so we're in that range. Beyond the heat affected zone is the lesser unaffected base metal, which might have gotten warm to the touch, but it didn't get warm enough to really change the microstructure. And if it did, it didn't cool fast enough to lock in any quench hardening effects, right? So welding is most concerned with the melted admixture, that new alloy we created between the two parent metals and the filler metal, and the solidification rate, right, that generates a certain heat affected zone and the subsequent microstructure after welding due to phase transformation and recrystallization, or the movement of metal atoms in the element when it's heated or cooled. Right, so one, we need to know the material type, the alloy, and the condition when we receive it. What alloy is it? What condition? Is it annealed? Is it heat treated? Is it cold worked? The heat of welding and many related processes have the ability to change mechanical, physical, and chemical properties of the common everyday metals that we use, not to mention if those are highly alloyed metals. So we need to know what's going to happen in the weld zones in order to choose the right approach and get the best possible results from welding. Depending on the specific alloy, steel, stainless, aluminum, or any other flavor, we need to pay attention to solidification and cooling rates so that we can prevent potential failures and other issues down the road. So we're going to discuss how heat flow from the arc and through the base metal is something that we need to consider in every weld, and more so in our more critical welding applications. And knowing how to handle any given material is the key difference between good and great. Do you know the difference between a discontinuity and a defect? Welding flaws or discontinuities are interruptions in the uniformity of a weld, which aren't necessarily defects, they're just differences. However, certain discontinuities or an accumulation of discontinuities become defects when the weld is compromised and can't perform in its intended application. Welding discontinuities tend to fall into three main categories. Those are related to design, to the welding process or the procedure or technique being used, and to the metallurgy. And you might have guessed it, we're going to focus on those related to metallurgy. Yeah, so of all these things that we see here, which are potential discontinuities that are commonly looked for when doing weld inspection, right? The ones we're going to be the most concerned with are distortion, cracking, and porosity, because they relate the most to metallurgy. So we already discussed the topic of thermal expansion, right? In the last module, metals expand when heated and contract when cooled. How much each material expands or contracts depends on their coefficient of thermal expansion. And in theory, we talked about even heating and cooling resulting in uniform changes to the material, right? It should grow in each direction equally. However, heat concentrates in different materials and shapes, so even heating and cooling is very difficult to achieve when welding, which is an uneven heating source to begin with, right? It's very localized, it's moving along a weld joint or seam, and we're going from near room temperature to the liquid state and back again in a matter of minutes and seconds, right? So if you can imagine, that metal around the arc is heating and expanding and then cooling as the arc moves on, which heats and expands a different area at a different time. And this uneven heating and cooling contributes to welding distortion, or the warping of the base materials around the weld. To compound matters, your weld is going to shrink about 10% of its average width, pulling further and stressing the metal around the weld as it solidifies and cools. This is called transverse distortion, right? Or it occurs perpendicular to your weld, right? It's pulling up like a banana on the edges adjacent to the weld. Transverse distortion is normally the most noticeable and severe, but you may also experience some longitudinal distortion as the weld shrinks along its length. It may pull back and shrink up or down depending on where the neutral axis is. You can use various methods to reduce or balance distortion, and we're going to talk about some of those in a minute. Because all metals distort, right? Now, something to pay attention to is stainless steel happens to be one of the worst because it has a low rate of thermal conductivity and a high rate of thermal expansion. Now, if that's a mind twister, just get your head around this. Think of stainless this way. You can heat it in one area, and it's going to hold that heat very local and not spread it all out like, say, aluminum would, right? Which is a super good conductor of heat. When you heat aluminum in one area, it gets hot all over the plate right now. Stainless is not going to do that. It's going to hold that heat. But in that smaller heated area, it's actually going to grow at a 10% higher rate than steel. So we're going to see more localized heating and retention and a lot more thermal expansion, which is going to make it distort a heck of a lot worse. And distortion is going to be one of the biggest issues we deal with in terms of metallurgy with stainless steels, even when we weld it right. Okay, so you seldom preheat stainless steels due to corrosion concerns, so we have to consider different ways of dealing with distortion when we're working with metals like stainless and even some grades of aluminum that we don't want to preheat. Let's talk about some methods to control distortion. Preheat and post-weld heat treating can slow the rate of cooling and promote more even heating and cooling cycles if the material and procedure allow for it, right? We have to be very careful preheating and post-weld heat treating on materials like stainless and aluminum. In general, we can get away with that, and it does promote some positive impact to our steel alloys, though. So you're going to see preheat and post-weld heating most often used with steel alloys. You can also clamp or restrain material, right? So we can force it and hold it into shape using backup bars and copper fixturing if possible. We can also pre-camber or pre-align a material so it distorts to its final dimension. And we can use heat sinking to remove heat quickly and minimize thermal expansion. And if we use the right weld joint, we can weld around the neutral axis, or we can balance out the distortion so that we don't see the banana effect in the case of a butt weld, for example, where we could weld that all from one side, and as we put multiple passes in, we're going to see that weld buckle up and see a ton of curvature to the plate because the weld is shrinking and pulling up on the outsides of the joint. So we're going to see a lot of distortion there. On the other hand, if we were to design a double V groove where we flip the part over and we put the second pass on the backside, that backside weld would balance the distortion from the front side, and we would end up with a flat plate. So again, joint design has a lot of influence on how that final weld is going to look. At the same time, welding parameters can also influence distortion. As a general rule, using more current and going faster will generate less distortion and less overall heat input, which considers the time factor in, right? The whole heat input concept. And keeping your weld narrow will result in less overall weld shrinkage, right? So the wider the weld, the more the distortion. The narrower the weld, the less distortion, following that 10% rule. We can use techniques like backstep welding, skip welding, and spot tacking, where we move around to control distortion and keep localized heating to a minimum. Now let's analyze porosity and inclusions. Porosity is trapped gas bubbles or pockets in solidified weld metal. Inclusions refer to solid, metallic, or non-metallic objects solidified in the weld metal. Both are evaluated based on size and distribution because they reduce the cross-sectional area of the weld and thereby reduce the strength, right? Where you see porosity or inclusions, there's actually less weld there, so it makes it weaker, not as strong in that area. Inclusions generally come from flux or electrode contamination, as in the flux dumped in the weld pool without burning or decomposing, and a slag may not have been formed or wasn't removed between passes. Tungsten electrodes can also get stuck in the puddle and break off, which is another type of an inclusion that we don't want to see in a weld. And porosity is actually caused by one thing, trapped gases of some sort that come from somewhere, right? In the case of some alloys, porosity is a result of the base metal. Perhaps the material contains sulfur, phosphorus, silicon, and is not a plain carbon steel and thereby may not have good weldability. Okay. If we determine it has good weldability, we could assume the base metal or the filler metal may have been contaminated and not properly cleaned or stored. We'll talk about sources of contamination in each material section so you'll know what to look for and what matters on each specific material as it comes to weld quality in your shop. So let's talk about the types of weld cracking that we're going to see. There's two types. Yep, just two types. Now they may show up slightly differently and look a little differently, but there's two main cracking types or cracking mechanisms in the metals that we work with. The one is, hey, you guessed it, weld cracking. And that's referring to when a weld cracks upon solidification or just soon after when it's hot and it cracks right down the weld center. This is the most common type of weld crack associated with aluminum alloys. It can be referred to as any of the above: centerline cracking, solidification cracking, hot short cracking. They all mean the same thing. How does that relate to metallurgy? Well, thankfully, solidification cracking isn't all that common in most metals, or base and filler metals have been formulated to resist it. So that's why we look up manufacturer recommendations as we match our filler metals, right? That's especially common in steel and stainless steel alloys. Those that are intended to be welded work together with the filler metals that are available. But filler metal selection has everything to do with your end results in terms of sensitive alloys, like aluminum. Right? And then there is the second type of cracking, base metal cracking. This is known as hydrogen cracking, cold cracking, delayed cracking, or underbead cracking because these cracks start in the heat affected zone. And they may continue through the weld or the base metal. This is a concern when you're welding heat treatable steel or stainless alloys where the heat affected zone got hot and then cooled too quickly and became brittle and then cracked as the metal around it expanded and contracted during heating and cooling. So we'll discuss each type of welding related crack and how welding metallurgy comes into play. As a review, in terms of welding, we're most concerned with the composition of the material, what's in it. The structure or internal arrangement of atoms and how heating and cooling may affect it is also important, as all metals respond to the heat of welding to some degree. But they respond differently based on the alloying elements, the internal structure, and the amount or rate of cooling, right? The amount of heat or rate of cooling. Knowing how to handle different alloys will come in handy when you're under the hood and under the gun. And as we discuss different metals and alloys, this list will grow and contain more considerations that you can take out into the shop. Now, let's wrap up our discussion by talking about some broad metal categories, right? Metals can be broadly grouped as ferrous or non-ferrous, or in other words, those that contain iron or are made from iron as their primary base metal, and those that are not. You might think this sounds broad and general, and it is, but it comes from our historic and widespread use of iron and steel alloys, which behave similarly when heated or welded. The discovery and use of other metals has created a growing group of non-ferrous alloys that all behave differently in some way. So the grouping makes sense from a top level standpoint. Does it behave like steel or does it have other properties? And this history explains why everything compares back to iron and steel alloys. Ferrous alloys include all steels and cast irons, carbon, stainless steel, high strength low alloy, tool steels are all ferrous alloys. They can generally be fusion welded together, provided proper filler metal, process, and technique are used, because they're iron-based and said to be metallurgically compatible. That doesn't mean you won't have issues, right? Try welding some tool steel and preventing it from cracking. It just means that it's possible to fusion weld them together because they're of like base metals. Non-ferrous alloys like aluminum, copper, and titanium are each distinct different metal groups. They are not iron-based. They do not behave like iron. Just like gold, silver, and platinum are different metals. They are not metallurgically compatible with iron or with other metals, right? So I can weld steel to steel, but I can't weld steel to aluminum or steel to gold. And thus, right, these types of metals cannot be fusion welded because they are not metallurgically compatible. They will not form an admixture, and upon solidification, they will crack or fail in some other way. Metals like steel and stainless steel, being both iron-based, aside from potential corrosion issues that might happen because of welding them together, the welds will be sufficient strength and not exhibit major discontinuities. So you can weld steel to stainless. But if you've ever tried to weld steel to aluminum or stainless to aluminum using an arc welding process, you know what I mean. So in those cases, when we do have to weld dissimilar metals, or we need a bond between dissimilar metals, we would use soldering, brazing, or some form of solid state welding like friction welding to achieve a bond that is, in many cases, as strong as a weld, even though there is no new admixture or alloy being formed. Congratulations, you've made it this far and now have a solid background of basic metallurgy and some welding fundamentals. In the next module, we'll discuss carbon steel metallurgy, the various categories, and when you need to pay attention in order to get good welding results because of the metallurgy. And we'll go over some common discontinuities so you can see how welding metallurgy applies in the real world. Stick around and stay tuned. Up next, Module 3 dives deep into carbon steels. Don't forget to test your knowledge by taking the quiz and earning your credential.